everyone, my name is Mira Karenina, and today I'm going to present you my research. The correlation of prevalence rate to the efficiency of the number of COVID-19 swab tests using virus split pool test method. Last July, Indonesia was overwhelmed by COVID's second wave. So that's why the government is trying to speed up tracing. One way to do this is by pool test. But since last year, there have been arguments that pool test is unsuitable when used in my city, Surabaya, because Surabaya has a high prevalence rate. But I wanted to know how high is high. So I picked that as my problem statement. I wanted to know how high the limit is. Is the binary split pool test method efficient if implemented in a population given its prevalence rate? Now, please keep in mind that this research is limited only to theoretical mathematics and not considering technical factors like reagent dilution or equipment accuracy that can lead to false positive or false negative results. For the research methodology, there will be two. The first one is deducing formula, and the second one is simulating data. Now, what is prevalence rate? Prevalence rate is the proportion of persons in a population who have a particular disease at a specified point of time or over a specified period of time. As for efficiency, in this research, efficiency is defined as the ratio of the number of COVID-19 PCR tests conducted using binary split pool test method to the number of samples. Now let's get into the binary split pool test. In a pool test, we mix the samples and then test it. Here, I represent the test result. I will be 1 if the result is positive, and it will be 0 if it's negative. If I is 1, that means at least one of the samples is positive, just like as shown in possibility 2, 3, and 4 here. If that is the case, then we will need to split it further by splitting it into 2 smaller pools, and so on and so on. But if the result is negative, like there, and we don't need to actually test it again, because we know for sure that none of the samples are positive. The result will always be either 0 or 1 if the pairing is 1. But it will be null if the pairing is 0 or null. But that only applies to the children node which has parents. For the very top stage which don't have parents, the result will always be either 0 or 1. Now, as for the number of children nodes, there will be no children node if the result is 0 or null. And there will be 2 children nodes if the result is 1. Now, in an email discussion with Mr. Untitled, whose article is used as my reference, he actually told me that I can remove one test if the parent is 1 and the left node is 0. Because in this condition, we know for sure that this right node is 1 even without test. So I eliminate one test for that condition. Now, in order to calculate the total number of tests needed in a tree, first we will need to sum up the number of tests needed in a stage. And then we calculate that starting from the top node, the children node of the top node, until the children node of the second last stage. And then we add 1 for the top node. Now, in this table here, I simulated all possible combinations of the initial samples of 4. You can see here that if the first stage result is 0, then we don't need to split it or test it any further. And we only need that one test. But for this combination, we test further when I is 1. And so for this combination, we need 5 tests. And there are 2 cases where the parent is 1 and the left node is 0. Right here and right here. So I can actually remove 2 tests, making it 3. And I simulated this and I recap that into the smaller paper in order to find the average number of tests. Now with that, we can now find the expected number of tests. Let's say I have the prevalence rate of 10%. And then I got the binomial distribution here. And for 40,000 samples, I only need around 20,000 samples. And that makes the efficiency of 0.53. And here is the efficiency result and setting the prevalence rate as a variable. I also extended my simulation by adding the initial pool of 8 samples and also 16 samples. And here is the chart version of that table. We can see here that the green line shows the threshold limit where the efficiency reaches 1. Beyond that, the pool test is no longer effective. And from that, we can see the prevalence rate of the intersection points, and then also the intersection points of each graph with the threshold point. And as a conclusion is, the most efficient binary split pool test method is the initial samples of 16 if the prevalence rate is lower than 6%, the initial samples of 8 if the prevalence rate is around 6 under 12%, and the initial samples of 4 if the prevalence rate is higher than 12%. Another conclusion is that the initial samples of 4 has the highest threshold. If the prevalence rate is below 31%, the binary split pool test method is still feasible. Now let's try to imply that in a real-world example. As of July 20, there are 10,000 confirmed cases of COVID in Surabaya, with a population of 2.8 million, and that gives the prevalence rate of 0.36%. And with this prevalence rate, I got this as my binomial distribution, and then I got this as the efficiency. Now, that efficiency, from this, we can see that the test can be finished approximately 4 times faster and cheaper. And for 40,000 samples, we can save almost $1 million. Now, we will try that and simulate it in a real-time situation. So, I will Google COVID here. So, let's say I want to look at the prevalence rate in Mexico. First, I will have to type in Mexico and then sort it per 1 million people. And as a result here, in Mexico, per 1 million people, there are roughly 27,000 cases. Now, we will put that into my simulation. We can see here that the prevalence rate is about 2%, and we got this as the binomial distribution. And it gives the efficiency of 0.33, and that means that it's approximately 3 times faster and also cheaper. Now that's it from me today. For my future work, I want to compare the efficiency with two-level pooling method. Thank you.
Thank you, Mira. Dr. Kim, Mr. Ivan, Miss Diana, some question.
It's your turn, Mr. Ivan. If you want to, yeah.
Yes, okay. So in your work, what we are proposing is to use the Dorfman method in order to reduce the number of analysis of samples that you have to perform in order to isolate the positive COVID cases. Is that right?
Yes, that is something like that.
So in one slide, you are proposing that you have to perform some PCR tests.
Yes, that is true.
Okay. Dorfman originally proposed this method in order to analyze blood samples. For example, you can extract 4 milliliters of blood, and if n is equal to 4, then you can have 4 samples of 1 milliliter of blood, and you can split, among any number of samples that you want. So my question for you would be, in the case of PCR, usually people use a cotton in order to get the sample. Could you propose a protocol in which you can guarantee that you have an homogeneous sample? For example, if you get a sample, how can you guarantee that you have four samples with the same amount of mucus, for example? Can you imagine a protocol?
Yes. So I am thinking that we can actually take, for example, I want to take 4 milliliters, and then I will take a certain number of samples, and then I will split that. So like I can add the protocol to take a certain number of the sample, so it can be sufficient for the pool testing. And I don't know if you get the concept of pool testing, right? But in pool test, we actually test the samples from different persons. So let's say I want to test 4 different persons, right? Then I will have to take the samples from each person A, person B, and C and D. Then I will mix that sample and then test it. It's like that. Pool test is like that. So it's actually from different persons, not from just one person.
Okay, that's all. Thank you very much.
Mr. Quick or Mr.
Right. Let me ask a question. Let me ask Mira. Now, can you say something about the limitation of this method?
Okay. So actually, for the limitations of this method of testing, let's see here. If the prevalence rate is higher than 31% here, then it means that we cannot actually imply that method because it will have more loss than normal individual tests. So if that's the case, so if for example, the prevalence rate is higher than 31%, then we'll actually have to conduct an individual test instead of pool test. Because in the prevalence rate, pool test will actually cost more, and it will take more tests than individual tests.
Mr. Quick, can you say something about the limitation of this method?
Okay.
what's the basic assumption behind this prevalence?
May you repeat your question, please?
Assumption that you made that you arrive at a criteria on the prevalence.
Oh, we can actually calculate the prevalence rate according. So we can actually look at the prevalence rate from the confirmed case in that region we want to apply the pool test, and we divide it by the population, the total population in that region.
Do you assume anything about the sensitivity of the test?
Sensitivity?
Of the test?
My calculations are based on ideal situations, so I can actually calculate the sensitivity or like that, because as I mentioned before in this, that I am not considering technical factors, for example, like region dilution or equipment accuracy.
There are other assumptions that you made.
There are none.
You don't assume that the infection among individuals have possess constant probability.
May you repeat the question, please?
That everybody has equal likelihood of getting infected.
Yes.
Which is not the case, because humans have different immunity tendency.
Yes, I didn't mention that because as I mentioned before, it's only limited to mathematics and considering on ideal conditions and assuming that it's all the same.
So what are your ideal conditions?
My ideal condition is the same. Every person has the same, like as you said, the immunity of the virus, and they're all the same, and assuming that it all can be detected in each person. And also, if I want to add, the ideal factors is also that the equipment are all accurate, so no false positive or false negative will be calculated here.
So earlier on you said that this method was not suitable. There were arguments against it. Do you want to elaborate?
If I had the chance to apply this in my city, I will actually consider that, because the cases here has quite a lot, and it will also help the government to speed up the tracing, and thus it will help the cases to be lowered.
Good. Perhaps someone else can take on.
Okay, I have one more question regarding to the efficiency on your simulation. The efficiency is a measure of the quality of the meaning shows an efficiency of 50%, and now is 26%, I think. Have you think a way to improve the efficiency? Because these tests are very expensive, no? So as more efficient will be the method, will be a lot of saving, no? So have you think how to improve the efficiency on the method or in this application?
Okay, so one way to actually to actually lower the efficiency is the prevalence rate itself, but we cannot control it. So I think maybe the technique. So the technique will also affect the efficiency. But here I only tested the binary split pool test method, and I got this as my efficiency. So yeah, I think the way to actually lower the efficiency is by using maybe another method of pool test. But actually, I have a method in mind. That is to increase the number of samples in a pool. So you can see here that the number of pool, the most is 16 samples. And if I were to increase that number of samples, the efficiency can actually go lower. But my research hasn't go there, because when I try to simulate more than 16, my computer crashed. So I cannot actually I haven't seen the result for the initial samples of higher than 16 samples.